Students, this lab is called An Investigation of Hess's Law. And in it, what we're going to do is perform 3 different reactions. Reaction 1 and reaction 2 will add together to produce the same chemicals as is seen in reaction 3. And what we're going to do is measure the heat energy released. All 3 of the reactions are exothermic, so we're releasing heat energy. And we're going to add together the heat released by reaction 1 and the heat released by reaction 2. And if Hess's law holds true, then the sum of those 2 heats of reaction should equal the heat of reaction for reaction 3. We'll see. It may or may not work out. In fact, it may be close, but not exactly spot on. To perform this, we have some hydrochloric acid, 1 molar concentration. We've got a calorimeter, which is simply a styrofoam cup with a lid. And the lid has a hole in it for the thermometer to be inserted. We have a 250 milliliter size graduated cylinder, some deionized water, a graduated cylinder, 100 milliliter size, along with a thermometer that will register degrees Celsius. We have a glass stirring rod to stir our solutions to get things dissolved. And then we have some solid sodium hydroxide, along with a scale and a weigh boat. So a handheld scale and weigh boat. All 3 of the reactions have their own procedure steps. So if you follow along on the handout, either on paper or online, we've got our equipment. And reaction 1, I'm going to write the equation on the board here. In reaction 1, we're simply dissolving sodium hydroxide. So we're going to start with solid sodium hydroxide in solution. And upon dissolving, we'll get sodium ions and hydroxide ions. To do this, we're going to find the mass of an empty styrofoam cup. So I'm going to take a handheld scale, turn it on, make sure we've got a 0 reading. And I'm going to place an empty, dry styrofoam cup on the scale. I'll record that mass, and it is 9.5 grams. There's a place on the lab report where you can record all of this data. And we'll walk through the calculations in a little bit. But we would be in data table for reaction 1. The mass of the empty cup is 9.5 grams. Then we're asked to pour approximately 150 milliliters into the cup and mass the cup in liquid. Now, you don't need to measure that exactly. What I'm going to do is take my bottle of deionized water, and I'm going to use my empty beaker as a rough measuring tool. So we're going to add about 150 milliliters of water to the cup, and I'm going to pour that into the cup. And now we can record the mass of the cup with water in it. And that works out to be 160 grams. So we'll record that in the data table as well. Then it asks us to record the temperature. So we're going to take our thermometer. We'll set that in the cup for a little bit, and we'll come back to that shortly. Meanwhile, we're going to do what it says after that. Carefully add about 4 grams of solid sodium hydroxide to the liquid. In order to measure out about 4 grams, it's hard to eyeball that. So I'm going to use the weigh boat, set it on the scale. And I'm going to scoop out using our bottle or a beaker with some sodium hydroxide in it. First of all, I'm going to hit the tare button after the whey boat is added. And I'm going to scoop out approximately 4 grams, a little more. There we go. Doesn't have to be exact. And then we'll put our cup back on the scale. At this point, our temperature should have stabilized. So let's note the temperature before I add the sodium hydroxide. Our initial temperature of the water is 22 degrees Celsius. So I'm going to now take the whey boat with sodium hydroxide. I'm going to carefully get all of it in. And then I can actually stir using the thermometer here. Stirring, stirring, stirring. In the meantime, as I'm stirring a little bit, I'm just going to pause momentarily to get the mass of the cup with liquid and now also the solid in it. And I'm registering 164.1 grams. So I'm going to record 164.1 grams as the mass of the liquid and the solid and the cup together. Then I'm going to keep stirring, 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 stirring. And what's happening is the temperature is rising. The process of dissolving sodium hydroxide is an exothermic process. Just how much heat is released, well, we're going to be able to calculate that when it gets to the calculation section. If I stir, 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 I'm going to wait just for a minute for the very highest temperature that can be achieved by this thermometer to be achieved, and that's the temperature that I'm going to record. In the meantime, while we're waiting for that very highest temperature, I'm kind of keeping an eye on it. I want to record the raw data that's of relevance. So here's a copy of our data tables. I'm going to kind of aim you over this way to reaction 1. In reaction 1, so far, we've recorded or have noted the mass of the empty cup, and that was 9.5 grams. We then added the amount of liquid specified and got 160 grams for the mass of the liquid and the cup. Then it says in the data table the mass of the liquid used. Well, to find that, we're just going to subtract 160 minus 9.5, and we get 150.5 grams. Then we were asked to add approximately 4 grams of sodium hydroxide. And then we added that in, stirred it, dissolved it, took the mass of that. That registered 164.1 grams. The next line in the data table says the mass of the liquid and the cup. Well, we've got that up here at the top. So you can just take whatever was in the top line of the data table and rewrite it here. The liquid and cup was 160. The mass of the solid and liquid and cup was 164.1. So if we subtract that out, we get a mass of the solid of 4.1 grams. Then we had an initial water temperature of 22 degrees Celsius. And I'm continuing to monitor the highest temperature achieved by the cup with the sodium hydroxide dissolved in it. And looks like we're getting right about 30 degrees Celsius. So I'm going to write that down as the highest temperature. And then asks us to, in the last line of the data table for reaction 1, it says record the change in temperature. Okay, final temp 30, initial temp 22. That change would be 8 degrees Celsius. Okay, now we're ready to move on to reaction 2 in the procedure. Come to this point. Notice that the last step of the procedure for reaction 1 says save the cup and its contents for use in reaction 2. In other words, we're not going to dump this out. We're going to do something else to it in reaction 2. So now reaction 2's procedure. It says add 150 milliliters of 1 molar hydrochloric acid to a beaker. Measure and record its temperature. Okay. Here's our 1 molar hydrochloric acid. Here's our beaker. I'm going to add 150 milliliters of the acid to the beaker. I'm just going to pour because it's a lot easier and faster to do it that way. We'll add a thermometer to that beaker so that we can record the temperature. It also asks us to measure and record the temperature of the contents of the styrofoam cup from reaction 1. So we're not done with that yet. So initial temperature of the HCl solution, we're looking at 22.5 degrees Celsius. Then I'm going to re-record and measure the temperature of the cup that held reaction 1. And it's starting to cool off a little bit. Remember, our highest temperature that we achieved at the end of reaction 1 was 30 degrees, but now we're at 27.8 degrees. Then in the procedure, it says pour the HCl solution into the styrofoam cup with the other liquid. Mask the liquid and the cup and record. So here I'm pouring the HCl solution into the styrofoam cup. I'm going to stir a little bit. And our temperature is shooting up. It says using the thermometer slowly and carefully stir until the temperature stabilizes. Record the temperature of the solution. We also need to find the mass of the liquid. Now, we're going to come into a little problem here because our electronic scale is not going to be sufficient to handle this mass. I'm getting an error reading. It's saying overload. So to address that, we're going to walk over to a different scale, a scale that can handle larger masses. So this type of scale, let me show you what this looks like. Move this here. This is called a triple beam balance. And the reason it's called a triple beam balance is it's a balance where you can push down on one side and you want the arrow to point at the 0 when it's completely balanced. And it has 3 beams, hence triple beam balance, that have little weight slots. It's a bit like a scale you might see at a doctor's office. And this can accommodate masses that are much higher than what this electronic scale that I was using for the first couple of mass readings is able to handle. But before I take the thermometer out to get the mass, I just want to record this final temperature. So in reaction to our final temp, looks to be holding at 29.2 degrees Celsius, 29.2. So now I'm going to remove the thermometer, set the solution on the triple beam balance, and I'm going to move the larger mass first. Okay, so it's somewhere between 300 and 400 grams. So I'm going to put the large mass back to 300. And okay, if I slide the medium size mass to the 10 grams, that causes it to tip up. Looks like it's really, really close here to 300, a little bit more. Okay. And we've got just about balanced here. So what I'm looking at is, does the floating balance point to the zero? And when it does, you've got the mass of the cup and its contents. Now that we've got that, we'll set this aside. And I think we're ready to calculate a little bit, or at least fill in the data table. So walking back to the board here. So in reaction to some of this data, we're just going to pull over or re-record from our first data table. It says at the top, the mass of the reaction 1 cup and contents and HCl solution. So this was the mass we just recorded. It was a little over 300 grams. I got 304 grams. And then it says the mass of the empty cup. Well, we already know that from reaction 1. I got 9.5 grams. So then if we subtract, okay, the mass of reaction 1 cup and contents plus HCl solution, should add that. Minus the mass of the cup, gives us a mass of the liquid used of 294.5 grams. So I just took this number minus this number to get this number. The initial temperature of the HCl, I had stuck a thermometer into the beaker there and got 22.5 degrees Celsius. The initial temperature of the reaction 1 cup, that was the same cup that we had used earlier, but it may have cooled off, and in our case it did. We got 27.8 degrees Celsius. And then in the data table, there's an interesting line here. It says the initial water temperature. And it says average the above two temps. So if we took roughly equal amounts of HCl and the reaction 1 cup, they were both had a volume of about 150 milliliters, then the initial temperature of the water you could assume to be the average of these two. So we'll take on our calculator 22.5 and we'll add to that 27.8, and then we'll divide that by 2. So if I take 22.5 plus 27.8, I get 50.3. Divide that by 2, and we get 25.15 degrees Celsius. The next line says final water temperature. So once we mixed the HCl solution with the reaction 1 cup contents, the highest temperature achieved was 29.2 degrees Celsius. So then we're going to calculate the change in temp. Well, that would just be the difference between the initial water temp, which is, again, the average of the above two temperatures, and the final temp. Now, since 25.15 is stated to the hundredths place, 29.2 is stated to the tenths place, I'm just going to treat it as 0.2. It's about a 4-degree difference. So the difference between 25 point roughly 2 and 29.2 is 4 degrees Celsius. Okay, now for reaction 3, we can just get rid of the contents of the cup. So we're going to restart, make up a new solution. So the first thing I'm going to do here, let me pause for just a minute. Okay, students, now let's take a look at reaction 3 of the Hess's Law Lab. For this one, we can empty out the contents of the styrofoam cup. So now I've got the cup re-emptied and we're ready to make a new solution. We're going to pour 150 milliliters of deionized water into the cup. I'm going to actually use the beaker to measure that. So I'm going to pour up to the 150 milliliter volume line. A little bit much. There we go. I already have the mass of the cup, so I'm going to add 150 milliliters of water. Next, I'm going to take some of the hydrochloric acid, and we're going to add another 150 milliliters. I'm using the same beaker to record the mass. I add to the 150 milliliter line. Add that to the cup. And kind of like before, if I attempt to use my electronic scale to measure the mass of the cup, I'm getting an overload reading. That means the mass of the cup is a little bit too big for the scale to be able to handle it. So we're going to use, once again, what's called the triple beam balance. This is a scale kind of like one that you would see at your doctor's office. You place the object that you're trying to measure on the platform, and then we're going to slide the big masses to the right until it just balances. So now I've over tipped it. Slide the smaller slider now. And if we read this, we've got a 200 gram plus 80 plus 8 or so. Actually, I'm more like 300, 310 or so. Then we're going to add approximately, as the procedure says, approximately 4 grams of solid sodium hydroxide. So for this, we can use the electronic scale because it won't overload the mass. So I'm going to set my empty weigh boat on the scale, hit the tare button, and then I'm going to scoop some sodium hydroxide onto the scale. And I'm adding about 3.5 grams. That's fine. That's close enough to 4. So now we've got approximately 4 grams of solid sodium hydroxide. At this point, I need to grab the initial temperature of the water and acid solution. So I'll let this sit just for a minute. In the meantime, I'll gather the lid for the calorimeter. And once we record this initial temperature, we're going to then add the sodium hydroxide, stir until it dissolves, and then we'll record the final temperature. For all of these reactions, again, we expect the temperature to rise. It's an exothermic reaction. So our initial temperature, I got 21.5 degrees Celsius. Now I'm going to add the sodium hydroxide. You can actually use the thermometer to stir. And I'm going to use the lid of the calorimeter so as to minimize the heat loss to the environment. Although when it comes time to discuss sources of error, of course, even with a decent calorimeter like a styrofoam cup, some heat is lost to the environment, and that definitely is a source of error. Just waiting for a minute for the final temperature to be achieved. We're going to record the highest temperature that this solution, this reaction mixture will get. And it's coming up to 29. So let's record that as 29 degrees Celsius. Okay, so now all of our data is complete. We'll take a moment to pause, and then we'll do the calculations part, which is really the most interesting part of this lab. Okay, students, let's talk about the calculations that go along with this lab, because they're a little more involved than a typical lab. I've translated onto the board the data points that we directly measured in lab. You'll need a calculator for this. In reaction 1, the mass of the liquid and the cup was 160 grams. The mass of the empty cup, in my example, is 9.5 grams. Now, you'll notice that reaction 2 asks for the empty cup's mass, and so does reaction 3. So you can just transfer the 9.5 grams all the way across. That won't change between the reactions, unless, of course, you switched up the cups, which we didn't do. Okay, in reaction 1, to get the mass of the liquid used, we'll subtract the mass of the liquid in cup minus the cup. That works out to be 150.5. That'll be an important data point. Then we added some solid, and we were asked to measure the mass of the solid, 164.1. If you then say, okay, we need to subtract from that the mass of the liquid in the cup, which is shown in the first line of the data table, we can just drop that number down of 160 grams. Then we can subtract 164.1 minus 160, and we get 4.1 grams of sodium hydroxide that we added. Lastly, we took the initial temperature of reaction 1 and the final temperature, and it warmed up. All of these reactions are exothermic. The question is just how exothermic are they? So we'll take 30 degrees minus 22 degrees. That gives us a change in temperature of 8 degrees Celsius. Okay, so how can we calculate delta H with that set of data? One thing that is going to be an important assumption is that for all of the solutions we use, we're going to assume that the specific heat of liquid water is also the specific heat of the solution. Now, that's a reasonable assumption because in just about every aqueous solution that exists, 99.9% of the molecules are, in fact, water molecules. So the specific heat of water with a little bit of sugar is almost the same as the specific heat of pure liquid water. So liquid water's specific heat is 4.18, and it's got the goofy units, joules per grams times degrees Celsius. The equation that will allow us to relate specific heat capacity and temperature change and mass to an amount of heat energy release is Q equals MC delta T. If you remember from our unit on calorimetry, this is one of our major equations. Furthermore, because all of our reactions are done under constant pressure, the enthalpy change for each reaction is equal to the heat energy released. So when we calculate heat, we indeed are calculating enthalpy, same thing. Okay, as long as it's done at constant pressure, which, you know what, unless you're drastically altering the atmospheric pressure, it's a pretty safe assumption. Okay, so what mass of liquid did we use? Well, let's refer to the data table. The third line down says 150.5. The specific heat capacity, we're going to assume that of the solution is the same as that of liquid water. So 4.18 joules per grams times degrees Celsius. And then we're going to multiply that by the temperature change, which is in the bottom line of the data table, 8 degrees Celsius. Now is when you would want to pull out your calculator. We're going to type in 150.5 times 4.18 times 8. It works out to be, if I'm rounding to the nearest whole number, I get 5,032 joules of heat energy. Now, it's going to be more convenient to state that as kilojoules, thousands of joules, because that's the more common unit that we use to express delta H. So if you just divide this number by 1,000, you can just restate that as 5.032 kilojoules. Now we're not quite done yet. There's one other really important step. That number of kilojoules of heat energy is the amount of heat released when 1 mole of sodium hydroxide reacts. However, we didn't have 1 mole of sodium hydroxide. We had 4.1 grams. So what we've got to do is convert that mass into moles, and then we'll divide the number of kilojoules by the number of moles that we have. When we convert mass into moles, we've got to use molar mass. So if you look up on the periodic table and add together the atomic weight of 1 atom of sodium, 1 atom of oxygen, and 1 atom of hydrogen, sorry. And let's keep it simple, round to the nearest whole number. So sodium is approximately 23, oxygen's 16, and hydrogen is 1. So 23 plus 16 plus 1, that's 40. So one more step here. If the molar mass of sodium hydroxide is 40, that means that 40 grams is equivalent to 1 mole. The way we wrote this conversion factor allows us to cross out grams. So now let's take the calculator out again. 4.1 divided by 40 gives us 0.1025 moles of sodium hydroxide, roughly 1/10 of a mole. So if roughly 5 kilojoules is released for a full mole, and we have 1/10 of a mole, just doing a little calculation, it'd be about 50, huh? Let's divide the number of kilojoules by the number of moles. So if we say, okay, delta H is measured in number of kilojoules per mole. So I'm going to write down 5.032 kilojoules and divide that by the number of moles we calculated. Our delta H for reaction 1, which I'll denote delta H subscript 1, works out to be if I round it to the 10th place, 49.1 kilojoules per mole. Okay, so that number is extremely important. That's one that I'm going to denote below the data table for reaction 1. So delta H1 was 49.1 kilojoules per mole. Let's go back to the data tables now and take a look at reaction 2. In reaction 2, if you remember, we prepared a solution of hydrochloric acid. We were asked to make a 150 milliliter solution, and we were going to add that together with the 150 milliliter solution of sodium hydroxide that we had already had in reaction 1. So we're taking equal volumes and mixing them together. And by the way, it's an acid and a base. When you react an acid with a base, a lot of heat energy is released. So in the data table, reaction 1 cup plus contents plus hydrochloric acid was 304 grams. The mass of the empty cup, 9.5 grams. So if we subtract that out, we get 294.5 grams for the liquid used, roughly double the amount of liquid as we had in reaction 1. Now, another interesting calculation here. We were asked in the procedure to measure the initial temperature of the hydrochloric acid before we mixed it with the stuff that was in the reaction 1 cup. We were also asked to measure the initial temperature of the reaction 1 cup. Now, you might say, isn't the temperature of the reaction 1 cup, shouldn't it just be the same as the final temperature from reaction 1? It should be close, but look, it might have cooled down. Indeed, I would expect maybe 5 to 10 minutes of time to have elapsed at room temperature while the beaker was sitting in room temperature. And it may have cooled off. So in fact, my final temp for reaction 1 is higher than the initial temperature of the reaction 1 cup that's found in reaction 2. It cooled off by a couple degrees. So that's all good. The interesting part is where they say initial water temperature, average of the above two. Since we mixed equal volumes of the acid and the sodium hydroxide solution, those temperatures, if you just average them, you should get the initial temperature of the mixture without having actually mixed it. So if you take out your calculator and add together 22.5 plus 27.8 and divide that by 2, we get 25.15. Let's call that 25.2. Keep it to the tens place. All right. The final temperature, highest temperature achieved by that mixture was 29.2. So the difference between the final temp and the initial temp, which agreed is a mathematically constructed number, was 4 degrees Celsius. Now we have the data we need to calculate the delta H for reaction 2. Same equations, students, same equations, but this time the mass is different. The mass of the liquid used is a little bit higher, about double what we had last time. The specific heat of liquid water is going to remain the same, but the temperature change is going to be a little bit different. So if we look at the data, our mass of liquid use is this time 294.5 instead of 150.5. Our temperature change now is not 8 degrees Celsius, it's 4 degrees Celsius. Notice that you had roughly double the mass of liquid and you had roughly half the change in temperature. That tells you something about the delta H. We'll see what the actual number works out to be, but I would guess if you have double the mass and half the temperature change, the delta H is probably pretty similar to what we saw with delta H1. Okay, so we crunch these numbers, multiply with your calculator, 294.5 times 4.18 times 4. I get 4,924 joules. And then like we did last time, it's more convenient to state that in kilojoules. So let's divide by 1,000. 4.924 kilojoules. Crucially, students, you didn't add any new solid. To make reaction 2 work, you use the same amount of sodium hydroxide as you had in reaction 1. In fact, all we did was dilute the solid solution. So the mass of the solid used is exactly the same, which means our number of moles of sodium hydroxide is exactly the same. The only thing that's going to be different this time is we're going to pull the number of kilojoules that we had just calculated, 4.924, and we're going to write that in the numerator of this calculation. And if we crunch those numbers, we'll get delta H2. So let's type in 4.924 divided by 0.1025. And I get 48.0 kilojoules per mole. And again, that's a really important number. I'm going to rewrite that number underneath the data table for reaction 2. All right, we're 2/3 of the way done here, students. Now for the last little bit. In reaction 3, we made a brand new solution. And this time, we had 310 grams of the liquid in the cup. The cup itself was 9.5 grams, just like before. If you subtract that out, we get a mass of liquid of 300.5. Then you made a brand new solution with a new batch of solid this time. When you measured the mass of the solid, liquid, and cup, we got 313.5. You'll notice the line below that says liquid in cup. Well, we have the liquid in cup from up above. Just rewrite that number, 310. And then we'll subtract 313.5 minus 310. Gives us a mass of solid used this time of 3.5 grams. The initial temperature of the solution was 21.5. Final temp 29, so it warmed up a decent amount. Change in temperature is 7.5 degrees Celsius. Okay, with that, we're going to do, once again, a Q equals MC delta T calculation. The mass this time can be found in the third line of the data table, 300.5. Once again, we're going to assume that the specific heat of water is the same as that of the solution we doctored up. Temperature change, 7.5 grams or degrees Celsius. We pull out our calculator at this point, punch in these numbers. You get 9,421, if I round to the nearest whole number, joules. And once again, let's state that in kilojoules by dividing by 1,000. 9.421 kilojoules. Now there's one last step before we can state the delta H. The mass of the solid used is not a full mole. It's quite a bit less than that. We use 3.5 grams of sodium hydroxide. So we've got to use the molar mass of sodium hydroxide once again. Now, if you remember from reaction 1, that molar mass was 40 grams, equal to 1 mole. So if we take 3.5 and divide by 40, we'll get the right number here. 0.0875 moles of sodium hydroxide. To state the delta H for reaction 3, we'll take the number of kilojoules and divide it by the number of moles. So it's always, delta H is a kilojoules per mole stated number. And I get 107, if I round that, I'd get, well, 107.7, let's say, kilojoules per mole. And I'm going to circle that and write it underneath the data table for reaction 3. Okay, so now we've got most of the hard work done, cleared and out of the way. But there's something that we should talk about. The idea of Hess's law is that when you add reactions together that make up an overall mechanism, the delta H's for each step in the mechanism should equal the overall delta H, or enthalpy change. Well, in this reaction, series of reactions, we deliberately set up the equation. We designed it so that reaction 1's equation is, when added together with reaction 2's equation, equals reaction 3. So let me erase here. If you look back at the introduction to the lab, reaction 1 was the breaking apart of sodium hydroxide into its ions. Reaction 2 was taking pre-existing sodium ions, hydroxide ions, and then adding in a strong acid, which exists as broken apart hydrogen and chloride ions. And we made sodium ions, chloride ions, and water. Well, if you look at our data tables now, the work that we've written down, the 49.1 kilojoules per mole for reaction 1, and the 48 kilojoules per mole for reaction 2, if you follow what we're doing, if we add the two equations together, and cross out whatever can cross out, we'll, let's see, sodium and hydroxide cross out. Well, what's not crossed out so far is reaction 3. So students, when you add together reactions 1 and 2, you get reaction 3. So then the question is, when you add the enthalpies together, does 49.1 plus 48 equal what we'd expect, which was for reaction 3, 107.7? Well, let's do a little math here. If you added together 49.1 and 48, we get 97.1. So we would expect the measured delta H, based on our adding together of delta H1 and 2, to get 97.1. What we actually got, our measured value, was 107.7. Now, students, you might say, oh, shoot, Hess's law must not have worked. But keep in mind that this is a lab where we're using imperfect equipment. Sources of error to talk about would probably be you were constantly leaking heat to the environment. Those styrofoam cups while good, fairly good at trapping heat energy, they're not perfect, even with a lid. 2, when you poured the contents of one cup into another, you didn't necessarily capture all of the heat energy. I mean, you're probably left with a warm beaker, but the contents got transferred to the styrofoam cup that was in reaction 2. So you're not capturing all of the energy. And to be within 10% of the expected value, so 107.7 is what you would expect. What we got was 97.1. I'd say, you know what, Hess's law is mostly supported, but not perfectly supported. And you'll have a chance to write about this in the lab report. So thank you for your attention and good luck writing up the report.